Awesome. Well, let's go ahead, and get started now that we've got a bunch of folks, and I'm sure we'll get some others joining. But yeah, welcome today, Dr. Gushu Li, who's at Penn and lots of extensive experience in quantum compilation, error correction, fault tolerance, like all of the important things that are happening in the industry today. And so, yeah, excited to hand it over to you to hear your perspective.
Okay, sure. Thank you. Thank you for the nice introduction. I'm very happy to here today to at this Quantum Wednesday to introduce some of our recent works on quantum error corrections and especially computer design or software infrastructures to help people automatically deploy and design deploy fault tolerant architectures. So before I start, let me start with a very brief introduction. I did my PhD at UC Santa Barbara back in December 2022, and then after that, I started my current job at assistant professor at Computer and Information Science Department at the University of Pennsylvania from January 2023. And currently, I mainly work on these three parts. The first part is now the focus of this group. We do almost everything about error correction these days. And previously, I do algorithmic compilation of foundations for Hamiltonian simulation applications. And I also do something on FPGA based device tuning and controls for quantum dot. But today we're going to focus on the first part. So, in terms of error corrections, what do we need if we want to, for example, run a quantum algorithm on a quantum computer with protected by quantum error correction? So, suppose you have a logical circuit you want to execute. First, you need to have quantum error correction protocol. You decide, okay, how are you going to encode logical informations with many physical qubits, and how are you going to implement all your logical operations for tolerantly, and how are you going to do your syndrome measurement? And then the next question is after you design, you have this schematic protocols. How do you really implement and deploy them onto hardwares, considering different hardware characteristics and constraints? And then, after you run things on your hardware, the syndrome data will be collected to a decoder, and then decoder will make a decision about how and where to make some error correction operations. So overall, these are the major error correction components. And you can see that it is a quite a large complicated system from the very high level theory on logically how are you going to design the code, and to how do you implement all these gadgets in the code protocol. How do you map things down to hardware, considering all this hardware constraints like qubit layout, timing, crosstalk, and different error models, all these kind of things, and finally putting everything together with control electronics, do your scheduling and decoding. So there are many details you need to consider for a large scale for tolerant quantum computers. And for now, we have seen a small scale prototyping experiments, maybe beyond the break even a point. But as systems continue to scale up, many design will soon become infeasible. So what we want to do for this computer-aided design for quantum error correction is similarly for classical computers, where you need compilers, design softwares to design your classical circuit and programming stuff. You also need such infrastructures for tolerant machine to automatically synthesize and optimize and do everything for you, and integrate everything together, and maybe do some co-design and ensure your implementation is correct. So essentially, that's the need for computer-aided design. So going back to this page, there are a couple things we are currently working on. The first one is how do we compile a logic circuit onto a fault-tolerant architecture? Suppose we already have the fault-tolerant protocols. And then, how after we have this fault tolerant protocols and gadgets, how are we going to implement everything onto hardware? And finally, how are we going to use softwares to synthesize new code structures and logical operations? We have like a bunch of works, but today we will spend most of the time like on this one on recent work on synthesizing code surgery operations. And I will briefly introduce our other works at the end of this talk. So let's start. So our work is called like Genesis. It's about like synthesizing code surgery protocols. So the paper is already like on archive. Like if you search for this keyword, you should be able to like see that quickly. So let's now talk about first talk about like what is code surgery. So in terms of like a code surgery, let's start from like something maybe you're more familiar with, which is lattice surgery, where like we use that to like enable logical operations, especially like a multi-logical qubit operations on service code. So essentially, like we are trying to implement like logical operations using just like a local measurement. So first, let's try to convert everything into like a graph-based like representation. So surface code, if you consider it as a graph, like or in the most precise language, it's like a two-chain, two complex chain. But for simplicity, like for computer science, like that, let's just say, okay, we have a graph, and the surface code has a graph of like which has like a very regular structure, where like we usually assign like let every edge to represent a physical qubit. And then like we use the vertices to represent like either like X checks or like faces to represent Z checks. And you can also like do like a vertex as Z checks, like a faces as X checks. This doesn't really matter, but let's just use this convention. And then like the logical operator, like a logical X operator is like a chain of like X operators like in one dimension. And Z like is a line of the operators in another like direction. And for lattice surgery on surface code, so essentially like we want to like concatenate like this two code, and finally our objective is to be able to measure a joint like logical operator XX on this like two surface code patches. So for lattice surgery, what we need to do is that okay, we first need to create two additional ancillary qubits in the middle. And then we expand the stabilizer structures in the middle by having, okay, again, like faces as vertices as the X checks and the faces as the D checks. Like, again, like suppose we are talking about CSS codes. For non-CSS code, like we can do some like we will be able to do some like local modifications to satisfy that. But again, let's first stay with CSS code. So there's some things we need to fix, like especially for local stabilizers, because for example, previously here is this stabilizer, but this will anti-commute with like other like new X stabilizers we are going to introduce. So what we are going to do is like initialize this qubit into zero state, and then expand the operators here to like make this like a new stabilizers commute with every other stabilizers. And then like you can see that after we doing this, the joint like a logical XX operator, basically like this six X operator, physical X operators now becomes a splitter of this new code. You can easily check that by multiplying like all these X checks marked red like in the middle together, and you will get this like a joint logical operators. So essentially, like we are converting the logical operators we want to measure into a stabilizer in a new code to be able to naturally measure them out during syndrome measurement of this new code. So this is the overall idea of like a lattice surgery. Let me see, where's my, okay. So but for code surgery, we want to do something like a similar for general QLDPC codes or general like a stabilizer code. So suppose like we have a logical operator or a code queue where like there's a logical operator we want to measure out like from this like code base. And what we need to do is that, okay, we want to attach an ancillary like a system onto this support of these logical operators, which again, as I said, we can represent like code structures as a graph, where like again like vertices are x checks and edges are qubits and the faces are z checks, or like later we will see that faces are like a cycle basis of essentially like a bunch of like basic cycles. You can multiply them to implement like arbitrary cycles in this graph. So this is like a cycle basis. And what we need to do is to like attach this graph onto this code base, and then all these like vertices are x checks like together with like the original like x operators on the code, and like cycles are the checks. And but there are some commitivity we want to be careful, because for example here suppose like we have another like a logical like a z stabilizer like interact with this x logical x operator, and we may have like some like anti-commutativity here. For example, like this stabilizer is not commute. This one this like vertex check does not commute with the new vertex check does not commute with the previous like these spiders here. So we need to have like a new like edge in the middle to like make them like commute with each other. So basically we need to have some local fix here. And general, like after we have this ancillary system, what we want to do is something like this. So for surface code, we need like this ancillary patch to connect like a code to implement two joint measurements to implement a C naught. And for general splitter code, what we need to do is something like this. So suppose we have like a two QRDBC code, like where like we want to jointly measure L1 and L2 as two logical operators on these two codes. We need to create like two ancillary systems, and then like connecting them with an like adapter in the middle, which is like just like connecting like those like edges, those vertices directly attached to the support here. And we are able to like make L1, L2 a new divider of this new code, so that we are able to like jointly implement the joint measurement of like L1 and L2. So this is how we are going to like this is our objective. But there are some things we need to consider. The first one is, how can we guarantee that our the construction of this like a new code structure is fault tolerant, or like more precisely, like the construction of this new code still have at least of the code distance of the original code. So let's see, what is the issue here? So suppose we are like attach, like there are a bunch of like, we have like a stabilizer, we have like a stabilizer here, like intersect with the logical operators like this, and the, it has a support of 6. And we have ancillary system like on top of that. And if you like multiply from this like a local stabilizer structure and the multiply of like those like stabilizer checks represented by the vertices and like faces, you will be able to end up getting something in the middle, which has like just intersect with just like two edges, which means your logic operator your polystring is now only active, like only non-trivial on just the two physical qubits, which means essentially like previously we have like a logical operators of distance 6, but now we have a logical operator of distance just 2, which means like our overall the code distance is decreased. So this is not something what we want. So we want that, okay, the structure we attach to it, no matter like how like what kind of like operator we're going to propagate through it, it always like maintains the weight of the stabilizer or like the code distance. So which means if we talk about translate this requirement into a graph property, which means like we need this graph expansion to be larger than 1, or let's say like the ratio between like if we like take a subset from like this graph, like the ratio between the outgoing edges and the inside vertices should always be larger than 1. Like suppose we are taking part of the just randomly select a couple of vertices here, and this is characterized by this number called Cheeger constant. Like a Cheeger constant basically represents the expansion property of this graph. and we need the Chica constant to be larger than 1. And overall, we need to we can if the graph is not like expansion do not have enough expansion, we can do something like this is by like thickening this graph by duplicating multiple layers, and then this can like boosting the relative expansion no matter where your logical operators come from the bottom, we can once we propagate through this more secant layers, we must be able to intercept with more edges in the middle, so that overall the fault tolerance can be the codistance can be guaranteed. Basically, if we have like a secant this layer, secant like arrow layers, we are going to boost the Chica constant by L beta. So essentially, like if we have a graph with Chica constant beta, and after we multiply it by arrow layers, we are going to be able to boost the relative expansion. So this is how we are going to manipulate this graph to be able to have enough fault tolerance. And another question is, how are we going to guarantee LDPC? Because we want our entire code after we attach this new code structures, it's still a low density parity checks, which means our every qubit should participate in at most a constant number of checks, and every check has only involved only a constant number of qubits. So in terms of the translating all these requirements to the graph properties, which means so for qubit degrees, for this graph, if you remember, we need some cycle basis as the checks. And how are we going to select the cycle basis? We're going to describe the quality of different cycle bases using this property called congestion. For example, in this graph, we can have this large pink block as a one cycle basis, and one green basis, another green basis, and one blue basis. Basically, this can be a graph basis to realize by multiplying them together, you can implement arbitrary cycles. But this basis has a relatively high congestion where one qubit, for example, this qubit is checked by 4 cycle basis by involving 4 similar checks if we select this cycle basis. Instead, if we have another a low congestion cycle basis like this, every qubit is involved in at most 2 the checks. So this makes this code more LDPC. And so once we do decongestions by creating a new layers, if you remember, in previous slides, we are able to boost the expansion by adding by duplicating this graph by multiple layers. And for congestion, we can also it also can be helped by to do decongestion by multiplying this graph by multiple layers. So what we can do is something like, suppose we have a graph and we just duplicating this graph, and then we can distribute this a congested cycle basis onto different layers where in each layer it is relatively low congestion. But in this case, we need to add some new cycles in the middle to be able to connecting this multiple layers together. And so essentially, we need to partition previously overlapping checks onto different layers, which is a more non-overlapping style. For check degree, which is this is a really relatively simple. If we have, for example, a large degree cycle check, we just add some edges in the middle to to adding some more physical qubits to be able to cut this large cycle into small triangles or polygons, and to reduce the size of the cycle check. So this is a couple of operations we are going to have. So now let's first review the existing protocols to construct this graph. This protocol was developed by Terry Yoder and Dominic Williamson from at IBM. So previously, mostly designed for their BB code architectures to enable logic operations on the for the BB code. So So essentially, first we need to add some like necessary edges to like manipulate local spider to make all the spiders commute. And then we need to like add a constant degree like a graph on attached to that and with expansion beta and say that okay we need like if the beta is like smaller than one we will need like to boost to secant this like a different secant this layer by like T1 times which is like 1 over beta to boost the expansion to make overall like the relative trigger constant is larger than one. This step is to guarantee that okay this we still have the same fault tolerance as the original code. And then like we need to make this code LDPC, which is that okay we need to be able to find like a low congestion cycle basis and calculate the number of like layers like a T2 to be able that is needed to decongestion. As I just say by like boosting multiple layers, we are able to like do the decongestion to reduce the the qubit weight. So, and then we can secant this graph by like a maximum like a T1 or T2, like which number is larger times. And then we finally we simulate the cycle checks by control by adding like additional like check, adding additional physical qubit in large cycle checks to be able to control the check degree. So this is how the baseline works. And now I'm going to talk about like how we are going to like derive a compiler to automatically optimize these steps. So the first optimization opportunity we observe comes from these first two steps where like a previous like approaches where like they guarantee the like fault tolerance by just after they do the spider commutations they add a constant degree like expander with expansion beta which where like these two steps are relatively independent. But what we find is that we can just like leverage the the edges we already have like when we're trying to like commute when we already added like for stepladder commutations to be able to like reduce the overhead when we are trying to construct the expansion graph. So overall idea is like this. So like suppose we have like an ancilla system like where we have like 18 qubits. You can see that in this graph we have like 18 edges here. And by adding like a bunch of like a new edges to this graph, where like this graph has like a trigger constant of like a beta equal beta larger than 0.5. We are able to guarantee that okay the final structure of this graph still have like shear constant larger than 0.5 but again like this basically ignores the contribution from the original code. So what we can do is that suppose like we have like after we do the stepladder combination, we already have some graph structures which have like a relatively like a lower like shear constant, and we can just add like a very few like edges to this graph to be able to make a graph that has like a larger shear constant, and then reduce the a lot of like the number of like ancilla qubits we need to introduce. So the first difficulties come from like how do we efficiently evaluate this expansion beta? The problem is that like calculating the shear constants, as you can imagine, like shear constant is relatively a global property of this graph, as with many like combinatorial optimization problems, like calculating the exactly calculating the shear constants is a bit hard problem. But graph theory told us that okay, we can actually bound the shear constant relatively easy by calculating the spectrum, the Blaney spectrum of this graph. And if we like have the graph lesson and we calculate the eigenvalues and the like second smallest like eigenvalue can be found like with like a relative polynomial time, and we have this triggers inequality that okay well we have this like inequality here like where like once we have a graph with a larger enough like smallest like eigenvalue we are able to know that okay the shear constant of we are able to have a lower bound of this shear constants. And remember that in this problem we just need the shear constants to be larger than something. So once we are able to like efficiently calculating the the spectrum, we are able to guarantee that okay our new new code is like fault tolerant or not. So we use like this like a cheap like a polynomial like a lambda 2 at the lower bound to bound the like NP hard Sugar constant. So so then like our overall like algorithm is like can be explained like this. So first we need to like fix the local computation by adding some edges. And then we add like edges to make all the we suppose like we have a graph have a maximum like degree 3 and a minimum degree 2. And a prior knowledge here is that usually like a random like a regular graph usually have like a strong a strong expansion. So which means like we want to like and add edges to this graph, but make this like close to some like uh, uh, regular graphs because as you can imagine, for regular graphs, no matter how you like pick up the subset of vertices, you can always expect like your outgoing edge, you have sufficient number of like outgoing edges. So we do this like sampling, a graph sampling approach like this. So essentially, like we add some edges, like among this vertices until it reaches like a 3 degree like a regular based on this property. Like we just if like a degree have like a lower like if a node have lower degree, we just have more probability to sample an edge among them. So and then like every time we sample, we add a new edge, we will like check the spectrum of this graph. Like if we are able to have like a eigenvalue that is above the threshold of the arbitrary constants, and then we can stop. Otherwise, like we just continue to make this a larger like degree graph. So if like we are not able to find, for example, a graph with sufficiently larger like eigenvalue, we are able to change it from like a 3 degree regular graph to a 4 degree regular graph, and by adding more edges until like this algorithm stop. Every time like we're going to increase the target degree by one. And so uh, so this is now the overall algorithm. Like we regularization to we randomly add edges to the graph and make it like regularized to a maximum degree, and then we increase the degree if like we are not able to reach the target expansion property. So this is how the overall the idea. In many cases we can stop early, but the one interesting one thing people may be like interested in is that okay, are we able to really able to sample a graph that has a strong expansion property? If like how likely will this algorithm will be able to stop? So we can prove that our strategy to sample a expander graph will like terminate with like close to one property. And we can model this like by like constructing the graph by increasing like adding independently sample like perfect matchings. Perfect matchings are like a randomly like just like a graph where like in those graphs where you just have like one edge is connecting to each vertex is just connecting to one edge, and the one edge just connecting like two vertices, and this is like a very simple like just it's like like a matching like one vertex from one set to another set. This is like called a perfect matching graph. And we call that GN1 is a uniformly random perfect matching graph on vertices. And the sampling like this, like R regular like a graph on n vertices can be modeled by like sampling like a randomly perfect matching graph like multiple times, and we are able to show that okay, this graph is expander with very high property, and exactly like this property is like one minus little o1, which means okay with very high probability like our algorithm can terminate, and in reality it terminates very fast. And overall, we use the eigenvalue to of this graph to bound the expansion, and we acted the sampling if the eigenvalue reach the expansion threshold we want to reach. So this is like the first part, how we're going to leverage the stabilizer combination graph to like help reduce the overhead when we are trying to construct the expander. And the next thing is about like how are we going to optimizing everything about like thickening and to balance the overhead of like expansion and the congestion. So
Let me just flag real quick while we're transitioning. There was a question in the chat about, is there an open source implementation or version of this available?
we don't have we don't like fully open source it yet, but if you're interested, like feel free to send me an email, and I we will give you the access to our code for now. We are going to open source everything in the future, but it may take some time before we finalize everything. But we can share with you some early versions.
Thanks.
Yes. So. The next thing is about how are you going to like dynamically control the expansion and and the congestion. And when we for example, sampling and adding edges to the graph, you can notice that okay, if you have like a more edges, you will relatively have like higher expansion because the edge when you have like more edges usually like we will have like more outgoing edges. We don't change the number of vertices here, so you will always have like a higher expansion. But when you add like a new edges, you always like add like a new cycles, so you will more likely to have like more congestions when we are trying to select a cycle basis. And if you have like less edges, the expansion will be lower, but the congestion will also be lower. And previously, we need T2 times for the decongestion, T1 times for increase the expansion. And usually, we will have this trade-off like this. And usually, for different random sampling cases, usually either like it has a higher decongestion layers we need, or like a higher layer number of layers we need for expansion. And we want to find a balance, for example, to exactly meet the need for like a decongestion and the expansion. So now I'm going to talk about our strategies to find the balance to sampling each new edge after this graph. So, for example, after we sampling each edges, we just calculate the expansion by calculating the eigenvalue, and then we can know how many layers we need to thickening given the current graph. And also, we can calculate what is the cycle basis here and the number of layers we need to do the deconstruction. And we keep monitoring this T1 and T2 during this process. As you can imagine, as we gradually have more edges in the graph, like T1 will decrease because the base graph will have more expansion properties and the less layers we need to boost the expansion. But for cycle basis, you can expect the T2 will going to increase during the graph expansion, during the graph sampling, because as you have new more cycles, you will need more layers to decongest the cycle basis. So T1 will decrease, T2 will increase, and we just stop when T1 reaches is equals to T2, and we can exit the sampling so that we are reach the balance point where we do not waste edges the number of thickenings on anything. So this is we already know how are we going to calculate the expansion by just calculating the eigenvalues. But now the question is how are we going to check the new cycle basis? So this is how are we going to do things. So in the baseline approach, what they need is that, okay, they have a base graph, and we can use this a Friedman-Hastings algorithm to find a relatively low congestion basis. And with a basis, with this a cycle basis, we can also have a spanning tree to connect everything. And then like after every time we add a new edge, like we add a new edge to this tree, we will have like a new cycles as a basis, and then we randomly drop like a one like a edge to maintain a structure, and then next time when we sample a new edge to this graph, we are able to generate another cycle. So this is how we are going to dynamically track the cycle basis. So uh, uh, how about the low congestion? And you can prove that like, the low congestions can be bounded by the diameter of this of the tree. And for a regular like a deregular for like a regular like random graph, we can almost sure that the diameter of the tree of this like a forest of this graph have like or expander always have like a logarithmic diameter, which means like the cycle of the any new cycle you generate by adding a new edge cannot will not be like have a very large cycle basis. Will not have a very long like a cycle length, which means okay we can have a new cycle, but the diameter of this expander may shift during the middle, but we can always like reset the tree at at a certain point, and then we run the like a Friedman-Hosting algorithm to reconstruct reconstruct a new like sampling tree to do this, and then we can then like segregate the layer, the T2 for T2 for decongestion, the new cycle basis. And again, like as we talk about, we exit our search by like when T1 is equals to T2. And overall, like this is the algorithm to maintain to track the cycle basis dynamically during the search process, and we will have like we will always like track the forest and cycle basis and everything together. And this is maybe a little bit hard to follow, but just to give you give you an overall idea like about like how are we going to maintain the balance of decongestions and like expansions, and for details feel free to check our papers. And for the last part, it is like relatively easy, and we just need to after we have like we do the thickening and do the decongestion, so we can like control the degree, and also like allocate the cycle basis to different layers. And if we have like accidentally have a very large like cycle, we just add some edges in the middle to do the cellulate to the like to the cycle, to the length of the cycle basis is something what we want. So overall, this is a graph synthesize and optimization framework where we have like a structure-aware graph expansion to sample the expander graph with like a small overhead, and then we control the expansion and congestion by like balancing the number of layers we need to thickening to augment the expansion and do the decongestion, and we have like some like local final fixes to constrain the check degree and the cubic degree. So so overall, what we do is that, okay, if you give me your stepladder code and the logical operators you want to measure, we are going to generate like a ancillary system like this attached to your like original code, and where you're able to like implement the resource efficient code surgery onto this new code by like promoting the logical operator into a stepladder of this new code. Okay, so now let's go to the evaluation part. Uh, we first evaluate the size of the, or essentially the number of ancillary qubits and the size, number of checks we need to do the code surgery for like every different qubit. Essentially, this is like the size of the, this characterizes the size of the like ancillary systems for base like arbitrary like subadder code. You can do it like on any like a subadder code you want. Even like we can work for non-CSS code, like, but I didn't talk about have time to talk about like how we're going to fix that. But it's just some very simple local transformations. And the baseline is IBM's like strategy use gauge fixing, where you can see that our the number at the front is the number of ancillary qubits we need, and the number here is the number of like stabilizer checks we need to have. And overall, we are able to significantly reduce the number of like ancillary qubits and the number of like additional stabilizer checks we need to implement. And on average, we're able to reduce like 85% of the resource overhead by like only using like a very few like additional hardware resources to implement this like a code surgery. And this is like the previous slide is just about the ancillary system, and here is the overall like a resource overhead to fully implement a joint logical measurement between like arbitrary two code. You can do something like between BB code and service code, between hybrid product code to service code, quantum tenor code to color code. Like you can do whatever you want. It's like it's like support arbitrary spider code. And this is like again like we can save a lot of like ancillary qubit and stabilizer checks. And this is the here DEG represent okay the maximum like the maximum number of checks each a qubit will participate, and the number of like the maximum of the like weight of the stabilizer with all the stabilizers here. So and the time represents the execution time of this synthesis process. And you can see that, okay, even for very large code instances, so we can find like this solution in a relatively short time. And actually, the first three like larger columns are like for to measure like individually like one joint like logical operator pairs between these two codes. The last row shows like if you want to implement all the like 24 joint X basis logical operations between like for example two BB codes. This is like the overall like size you need to have. Okay, so this in our result is even like better than like a recent like a high rate parallel like logical operation constructions. So this is the result. And so what about the logical error rate? So we simulate the logical error rates like for this like single like ancillary systems and the joint measurement like between like arbitrary like between like some code pairs. And you can see that usually most of the time like our result just overlaps with the baseline. We have like we can see that the identical logical error rate, but keep in mind that like we're using much fewer hardware resources to be able to reach the same logical error rate. So this is the circuit level noise simulation. And in terms of like scalability, so even for like a service code with like a 10,000 physical qubits and a distance of 100, we are able to still like maintain a relatively short search time. And actually, this search time does not depend on the code structures, which is like it only like depend on some like local stabilizer structures, which is like almost like people have already showed that it is almost the same for every like all the LDPC codes. So this is the code surgery work I hope to like focus on today. And after that, I'm going to like talk about some other briefly quickly go through some other stuffs we have been doing. The first one is about like how are we going to do topological compilation from logical circuits to like service code. Like for service code, when you do like especially on solid state quantum devices, when you do like logical operations, you need like this pipe diagram represented like lattice surgery operations to implement like a synodic gate like this. And for service code, there's one interesting thing is that after you have like a pipe diagram in the space-time volume, and no matter how you manipulate that, like once you have the same topological structure, you're actually doing the same thing. So here, like if we do not like consider like topological properties during compilation, we want to compile like this three synodic gate, we will end up getting something like this, but which have like a relatively high like space-time volume overhead. But if we are able to like manipulate, but we can also like convert this circuit into the calculus diagram and manipulate this thing into a more compact structure, and finally end up getting something like this. Like this thing, like essentially it is doing the same thing as the previous one, but it is using like a much smaller like space-time volume. So we developed this TOPLS compiler to enable this topological considerations in compiler operations for lattice surgery on like service code. And it is like a good compiler for like optimize very large scale like pipe diagrams, and it is now like a fully public released under the TQEC organization. And this is the result, like compared with like some recent baselines, we're able to reduce the space-time volume like to a large amount. And this is the first thing. The second thing is about like how are we going to implement optimize the code implementations. And the specific work is about like how are we going to schedule the syndrome measurement circuit. For error correction code, like when you do the syndrome measurement, you need to measure the generators of the stabilizer group like repeatedly, and actually like executing this like such syndrome measurement circuit takes most of the times in like fault tolerant quantum computation. And the circuit to implement this syndrome measurement is not unique. There are a lot of like flexibilities. You can exchange the orders inside the stabilizer measurement, and also like how are you going to manage the stable element, like the order between like different stabilizers is also not unique. And but the important thing is that the different orders you use to do the syndrome measurement, especially if you are using like a single ancilla syndrome measurement, like the order matters a lot because these hook arrows happening on the ancilla qubits will propagate to like multiple data qubits, and different orders of syndrome measurement will let the hook arrows propagate to different patterns. Like here is like a profiling experiment. Like for surface code, if you use like a Google's order, like NZ order for different X and D stabilizers, you will and compare them with a trivial order where like you use the same like a syndrome measurement order for all patches, you will see a like one orders of magnitude of like a logic error rate in your noise simulation. The reason is that okay, the different orders will let the arrows propagate to different vertices to different directions. Like in Goose order, like the arrows will propagate like vertically, but in the trivial order, the arrows will propagate like horizontally. And in service code, like the logical operators is also like lies horizontally. So this like a propagation will look like more like a real logical operator, so that the decoder is more likely to make a mistake here. So the key idea is that okay, we want to design this scheduler that like try to schedule this syndrome measurement so to let the hook error propagate to something that a decoder can correctly like decode. So we have this pipelines like by like letting the decoder to try different noise simulation of the like syndrome measurement trails, and try to learn how to schedule the syndrome measurement so that the hook error propagates to correctable error patterns. And we have a lot of results in our paper, but something we want to highlight is that like for some existing constructions, like for IBM's BB code, we are able to under this noise model and under this like decoders, we are able to like even find some like schedulings that have like even lower logic error rate compared with IBM's manual design with like syndrome measurement scheduling even with the lowest depths. And for Google's order, like if you are talking about like just the uniform error models, and then we can at most like just matches like Google's order's performance. But when the like error like have like when we have a non-uniform error, which is very common, we will be able to find some like better schedulings compared with like Google's scheduling even for service code. And finally, like I can spend like 1 minute talk about the verification of fault tolerance work, where like Brad have actually helped us like develop the pattern wrapper for our tools. So in terms of like a fault tolerance, we're actually tracking like how error propagate during the implementation of the different error correction gadgets, and we want to care about if like one error happening in the middle will propagate to, for example, multiple errors. And finally, in the data qubits, and we want to be able to like reason about this error propagation, because this like heavily like will affect the effective like distance of your code, and the non-fault tolerant and fault tolerant like behavior can be very different. For creating gadgets, some gadgets are relatively easy to learn about. For example, if you have like a transversal like a gate or transversal logic gate or transversal CNOT, it's very easy to see. Okay, this implementation is must be fault tolerant. But for other like more complicated like gadgets, it's very hard to see. Okay, it involves like many qubits with like complex interactions. It's very hard to reason about okay whether they are fault tolerant or not. So we developed this symbolic execution engine. It takes like your like a Clifford circuit, like QEC gadget implementation at the input, and then run a symbolic execution through this circuit. It's like you can consider it like a symbolic version of Steam with like a symbolic error injections. And then we you can also write down the conditions of like of being fault tolerance for this like different gadgets. And then like the SMT solver will check okay whether like the symbolic execution result satisfies the conditions of being fault tolerant. If so, it can guarantee that okay, your implementation is fault tolerant, or it will give you some examples of okay, whether like in what cases in what error patterns like your implementation is not fault tolerant. And there are some interesting patterns we actually see during this development. For example, for cache state propagation, we can find that okay by just changing the locations of the parity checks, you can have like either a non-fault tolerant cache state propagation or fault tolerant cache state propagations. And also like you can find okay if you have enough like parity checks in your cache state propagations, and also if your syndrome measurement ordering is good or not. And currently, like this tool is able to accommodate circuit like with up to like hundreds of like physical qubits and maybe a few thousand gates in I would say like a reasonable time, maybe a couple of days. Ultimately, like all these kinds of like automated like verification tools are usually not very scalable, to be honest. But at the end, you can consider it as like a circuit level distance calculator. So okay, so this is I quickly go through some other works of our group. Let me go back to these slides, and I'm happy to take some questions, especially about the first work on code surgery. Thanks. And thanks everyone for your attention.
And thank you for the great talk. I'll open it up. I have a question or two, but I'll see if there's anyone else that has one. Not yet. Okay, so I'll ask one of my questions. So you may have covered this a little bit, but if you for the first technique that you shared, how should I think about how that maybe relates to decoder design and other, maybe even from a performance perspective? So maybe like, is there another layer of co-design that you're imagining maybe be between these layers? Because the way I heard the presentation is you have some very strong co-design techniques that overlap a little bit, but they're kind of targeting different aspects. Is there a way that you've already started to think about kind of the co-design that kind of sits on top of all this currently?
Yeah, sure. So I can briefly expand something here. For example, originally this technique was developed by IBM to be able to guide, I think, their logical processor unit design to be able to concatenate like different BB code blocks. And in terms of like hardware design, like if you are going to implement this ancillary system on hardware, there will be like some limitations on like IBMs can do like some sort of like high degree physical qubit connections, and also a little bit like a long range like a qubit interconnections, but there is some limit there. For example, if we can co-design like the generation of this like code surgery protocols with the but also considering the hardware constraints and the cost when we are trying to implement this like new code structures on hardware, maybe probably we can help like synthesize like cost efficient our hardware like implementation like which is easy to be fabricated, or cost efficient hardware implementation of this surgery protocols. So this is like one overall idea. The decoder is also something interesting to consider, because for now we just use like a standard like a BPOSD decoder which like basically works for arbitrary QLDPC code, and here like for our new code, like it is also a QLDPC code, but we can also have, for example, dedicated decoders to on this like a diff like a code during this code deformation process, because during the process of this like a new construction, actually the code structure is like dynamically changing during this surgery process, and how are we going to do decoding during the like logical operations is also, I think, a problem. Previously, I think most of the code designs and decoder designs are like mostly for like memory experiments, and how are we going to do that for this kind of during this logical operations is also a problem we can properly code design.
Thank you. Any other questions?
Yeah, maybe a quick question. Thanks for the very nice talk. So maybe you have covered this a little bit in your talk, but I'm wondering, what's the performance for this code surgery framework in the presence of different noise model, like different error models? Like for example, if you have a different type of correlate, like error resource, and different type of like correlate errors, like could you comment a little bit on this?
Okay, so currently like we on like we do this like circuit level noise simulation by just inject like I think independent deployation
Mm-hmm.
noise models on
I
for
see.
every gate and every like idle locations as the coherence. Uh, we did not like test too much on like correlate on correlated noise, because as you can imagine, for even for like current simulation structures, implementing correlated noise in Steam is not
Yeah.
a
Yeah.
trivial effort, to be honest.
Mm-hmm.
I'm sorry for that. So. Uh, I would expect things can be similar in our system, because actually we are using like fewer hardware resources compared with the baseline. But overall, like if you need like a fine-grained like simulation or specific system, like we will need the like a fine-grained or precise hardware like a noise model profile on your like targeted system. Yeah.
Yeah. Okay.
Usually we don't have that. That's
Mm-hmm.
a
Yeah.
problem. Yeah.
Got it. Yeah. Thank you very much.
We're about at time, but yeah, any last questions? If not, all right, yeah. Thank you again, Gushu. Really great talk. I think
Thank
based
you.
on the chat, there's a lot of people who are going to be reading the paper and kind of
Yeah,
looking
yeah.
at the
I'm very happy
packages.
to
So yeah,
share our recent results on logical operation constructions.
yeah, great to hear. So yeah, thank you again. Appreciate it.
Thank
Thank
you.
you.